Hello dear friends, this is Dr. Diptesh Patel and I'll be teaching you advanced internal combustion engine. For this video session, we are going to start a new chapter called ideal models of engine cycles, in which we are going to see the various different types of the models of the engine cycles. Those are considered as ideal models such as Otto cycle, diesel cycle, dual cycle. We are also going to see the actual models as well in this chapter. So particular for this video session, we are going to see the ideal models of Otto cycle and the ideal model of diesel cycle. So let's start with the Otto cycle. First of all, Otto cycle is a thermodynamic cycle which is used for SI or petrol engine. So spark ignition or a petrol engine, we use the Otto cycle. It consists of the four different processes. Couple of them are reversible adiabatic compression and expansion process, and the remaining two are constant volume heat addition process and constant volume heat rejection process. So this process makes the whole cycle. Now as you can see over the cycles of the Otto, let's begin with the process 1 to 2. 1 to 2 is an isentropic compression process in which the fresh charge of mixture of air and fuel is compressed with the help of piston. Due to that, the pressure would increase. It also increases the temperature but reduces the volume. Then after 2 to 3 is a constant volume process in which the heat is added. So basically the air and fuel mixture is ignited with the help of the spark plug during this process. During this process the volume is remain constant, however the pressure and temperature both increase to its peak point. Then after 3 to 4 is a isentropic expansion process. Once the combustion takes place, the power is utilized to run the engine and the other parts of the automobile vehicles that would takes place during the expansion process. So 3 to 4 is a isentropic expansion process. During this process entropy is assumed to be remain constant, and 4 to 1 is again constant volume heat rejection process in which the gases which has been the products of the combustion is removed from the engine. So heat is being rejected from the engine at constant volume. Now we are going to see the efficiency, work done, the mean effective pressure of Otto cycle. So first of all, as we know, the heat is supplied in between 2 to 3 and heat is rejected in between 4 to 1. So heat supplied, if I want to calculate heat supplied, then I would say heat supplied Qs is equal to Cv T3 minus T2, because it is at constant volume. Similarly, heat rejection is equal to Cv T4 minus T1. Also the compression ratio, the pressure that has been raised during the compression from 1 to 2, compression ratio Rk can be written as V1 upon V2. And therefore, if I want to calculate the thermal efficiency, I would say thermal efficiency is equal to input divided by output. Now our input would be the amount of heat that is being supplied minus the amount of heat that is being rejected. So Qs minus Qr, and our output is a heat supplied Qs. Now if I want to simplify that, that can be written as Cv T3 minus T2 minus Cv T4 minus T1 divided by Cv T3 minus T2, and that can be written as 1 minus T4 minus T1 divided by T3 minus T2, because Cv is taken out, those are commons and they can be eliminated. So here the thermal efficiency of Otto cycle is 1 minus T4 minus T1 divided by T3 minus T2. Now let's simplify it a little bit more. So as we know, the process 1 to 2 is a adiabatic compression process. It's a isentropic process, and therefore we are going to use the isentropic relations, and those relations are T2 upon T1 is equal to V1 upon V2 raised to gamma minus 1, and therefore T2 can be written as T1 into Rk raised to gamma minus 1, where Rk is a compression ratio. Similarly, in adiabatic expansion process, which is 3 to 4, during that time the entropies also remain constant, so we are going to use the isentropic relations for those processes as well, and that is T4 upon T3 is equal to V3 upon V4 raised to gamma minus 1 up. Therefore, that can also be written as V2 upon V1 raised to gamma minus 1, because we know that V2 is equal to V3 and V4 is equal to V1, and therefore T3 is equal to T4 into Rk raised to gamma minus 1. Now let's put these values in the equations of thermal efficiency, and thermal efficiency can be written as 1 minus T4 minus T1 divided by T4 into Rk raised to gamma minus 1 minus T1 Rk raised to gamma minus 1, and that would be 1 minus 1 upon Rk raised to gamma minus 1. So this is what the efficiency is. Now let's move forward to the work done. Here we are going to use the pressure ratio, that is Rp P3 upon P2, which is equal to P4 upon P1, and that can be written as P2 upon P1, which is equal to P3 upon P4, which is equal to V1 upon V2 raised to gamma, that is equal to Rk raised to gamma, because we know that that is a compression ratio. Now let's make the formula for work done, that is P3 V3 minus P4 V4 divided by gamma minus 1 minus P2 V2 minus P1 V1 raised to gamma divided by gamma minus 1, and that can be written as, we are going to take the 1 upon gamma minus 1 common out, so that can be written as 1 upon gamma minus 1 P4 V4 into P3 V3 divided by P4 V4 minus 1 minus P1 V1 P2 V2 divided by P1 V1 minus 1, and that is equal to 1 upon gamma minus 1 P4 V1 Rk raised to gamma minus 1 minus 1 minus P1 V1 Rk raised to gamma minus 1 minus 1. So that is work done. So that can be further written as P1 V1 divided by gamma minus 1 into Rp into Rk raised to gamma minus 1 minus 1 minus Rk raised to gamma minus 1 minus 1. That can be written as P1 V1 upon gamma minus 1 inside the bracket Rk raised to gamma minus 1 minus 1 into Rp minus 1. So that is the formula to calculate the work done in Otto cycle. Now let's move forward for the mean effective pressure. Now mean effective pressure PM is equal to work done divided by swept volume. We know that it's a work done divided by swept volume. So that can be even further written as work done divided by swept volume is a V1 minus V2. Okay, V1 minus V2. So the mean effective pressure can be P1 V1 upon gamma minus 1 into Rk raised to gamma minus 1 minus 1 Rp minus 1 divided by V1 upon V2. So here we are going to put the equations of work done straight away, that would be divided by swept volume, that is V1 minus V2, and that is equal to P1 Rk inside the bracket Rk raised to gamma minus 1 minus 1 Rp minus 1 divided by gamma minus 1 upon into Rk minus 1. So that is the mean effective pressure in Otto cycle. Now let's move forward for the diesel cycle. We know that their workings are completely different. Here it's a compression ignition engine in which the fuel is ignited instantaneously because of the pressure. So diesel cycle works a little bit differently than the Otto cycle. So basically diesel cycle, it's a thermodynamic cycle for CI and diesel engine. It consists of a reversible adiabatic compression process, one reversible adiabatic expansion process, one constant pressure heat addition process, and one constant volume heat rejection process. So these are the 4 different processes of the diesel cycle. Now let's go through the diesel cycle. Here you can see 1 to 2 is an isentropic process in which the entropy is assumed to be remain constant, volume is reduced from V1 to V2 while the pressure and temperature both increase to its peak point. Then after, heat that is being added in between 2 to 3. 2 to 3 is a constant pressure heat addition process, which is different than the petrol engine. In petrol engine we had the constant volume heat addition process. It's a constant pressure heat addition process. Then after 3 to 4 is again isentropic expansion process, in which the gases are released from the engine, and 4 to 1 is the constant volume heat rejection process, in which the gases are removed into the atmosphere. So the only difference between the Otto and diesel cycle are the process 2 to 3 or heat addition process. In petrol engine it's a constant volume heat addition process. In diesel engine it's a constant pressure heat addition process. Now let's go through the efficiency, work done, and mean effective pressure of the diesel engine. So first of all, diesel engine, in which heat supplied can be calculated in between 2 to 3. So heat supplied is equal to Cp T3 minus T2. We are going to use the Cp because heat is added at constant pressure. Heat rejections is Cv T4 minus T1. Here the compression ratio would be remain same, Rk V1 upon V2, while cutoff ratio Rc is taken in between volume from 2 to 3. So it is V3 to V2. It's a ratio of V3 to V2. That would be considered as a cutoff ratio. Efficiency, if I want to calculate the thermal efficiency, then definitely heat supplied minus heat rejected divided by heat supplied. So that can be written as Cp T3 minus T2 minus Cv T4 minus T1 divided by Cp T3 minus T2, which is equal to 1 minus 1 upon gamma T4 minus T1 divided by T3 minus T2. We know that Cp upon Cv is gamma, so that can be written here. Right. Now let's simplify the efficiency, in which we know that there are two different isentropic processes, process 1 to 2 and process 3 to 4. So we are going to use the isentropic relationship for both of them. So let's do that for compression process 1 to 2, which is written as T2 upon T1 is equal to V1 upon V2 raised to gamma minus 1, and we know that V1 upon V2 is a compression ratio Rk. So therefore this can be written as T2 is equal to T1 into Rk raised to gamma minus 1. Similarly, for expansion process we can write the same thing again, but before that we are going to see the process 2 to 3, which is the constant pressure heat addition process, in which we are going to use cutoff ratio. So here T3 upon T2, which is equal to V3 upon V2, that is equal to Rc, that is cutoff ratio, and therefore T3 is equal to T2 into Rc, or which is equal to T1 into Rk raised to gamma minus 1 into Rc, because we know that T2 is equal to T1 Rk raised to gamma minus 1. Similarly, for adiabatic expansion process 3 to 4, we know that the isentropic relations are T4 upon T3, that is equal to V3 upon V4 raised to gamma minus 1, and that is equal to, with here we are going to add V2 on the both side, so that is equal to V3 upon V2 into V2 upon V4 raised to gamma minus 1, and that is equal to Rc raised to gamma minus 1 into 1 upon Rk raised to gamma minus 1. So that is the adiabatic expansion process. Now here we are going to simplify it a little bit more, and that for T4 can be written as T3 into Rc raised to gamma minus 1 into 1 upon Rk raised to gamma minus 1, which is equal to T1 Rk raised to gamma minus 1 into Rc raised to gamma minus 1 into 1 upon Rk raised to gamma minus 1, which is equal to T1 into Rc. Here the whole terms will be eliminated. Okay, both Rk raised to gamma minus 1 would be eliminated here. Also the Rc would left behind, so we have T4 is equal to T1 into Rc. Now let's go back to the thermal efficiency. The thermal efficiency was 1 minus 1 upon gamma T4 minus T1 divided by T3 minus T2. So let's put the values of the various terms here, and that can be and rewrite it again. So that can be rewrite as 1 minus 1 upon gamma Rk raised to gamma minus 1 into Rc raised to gamma minus 1 upon Rc minus 1. So that is the thermal efficiency. Now let's go for the work done. Work done, W is equal to P2 into V3 minus V2 plus P3V3 minus P4V4 upon gamma minus 1 minus P2V2 minus P1V1 upon gamma minus 1. That can be rewrite as P2 RCV2 minus V2 plus P2 RCV2 minus P4 RKV2 divided by gamma minus 1 minus P2 V4 minus P1 RK V2 divided by gamma minus 1, because we know that V1 is equal to V4. Further simplification would lead us to P2 V2 into RC minus 1 gamma minus 1 plus RC minus RC raised to gamma into RK raised to gamma minus gamma into RK minus inside the bracket 1 minus RK raised to 1 minus gamma upon gamma minus 1, and therefore that would be P1 V1 RK raised to gamma minus 1 inside the bracket gamma RC minus 1 minus RK raised to 1 minus gamma into RC raised to gamma minus 1 upon gamma minus 1. So that would be the work done of the diesel cycle. Now let's move forward to the mean effective pressure. Mean effective pressure for the diesel cycle is P1 V1 RK raised to gamma minus 1 inside the bracket gamma inside the bracket RC minus 1 minus RK raised to 1 minus gamma into RC raised to gamma minus 1, and the whole term is divided by gamma minus 1, and that would be divided with the V1 minus V2, that is the swept volume. For the simplifications, we can go through the mean effective pressure is equal to P1 RK raised to gamma inside the bracket gamma RC minus 1 minus RK raised to 1 minus gamma into RC raised to gamma minus 1, and the whole term is divided by gamma minus 1 into RK minus 1. So that is the mean effective pressure of the diesel cycle. So yeah, for today's session we have gone through the ideal models for both Otto and diesel cycle. In the next video session we are going to see some more ideal models of the engine cycles, and we are also going to see the actual models of the IC engine. Thank you very much.